So let us begin. The first speaker today is Gabriel Wong from Fudan University, who will tell us about entanglement entropy and edge modes in topological string theory.
Thank you very much for the invitation to talk. So I changed my title a bit to Generalized Entropy in Topological String Theory, based on some papers posted recently with these collaborators here. So my motivation comes from the ADS-CFT and the holographic entanglement entropy formula, which tells us the entanglement entropy of a boundary subregion V is dual to the generalized entropy in the bulk. It has a leading area term that looks like Bekenstein-Hawking entropy, which is an area of a Fortune region of this extremal surface, and a bulk quantum correction. And it's the basis for our understanding of how space-time emerges from quantum entanglement. Now, we want to understand what is the bulk string theory microscopic interpretation of this area term. It's interesting because we think that it measures the entanglement that makes up the space-time itself. Our main inspiration for thinking about this comes from Susskind and Uglum, who proposed that Bekenstein-Hawking entropy is the entanglement entropy of strings across the horizon. The idea is that these closed strings get cut by the horizon of the black hole into open strings, which are entangled, and the Bekenstein-Hawking entropy is the entanglement of these string edge modes at the endpoints of the open strings. Now, I want to say more about what they did. They considered string theory on a conical manifold, which is an analog of the cigar geometry with a conical singularity here. And we just pretend that the string theory path integral on this conical manifold is like a thermal partition function, and write down the thermal entropy. This is generalized entropy formula. And we find that the area term comes from the sphere diagram that's intersected by this conical singularity. The idea for interpreting this in a canonical fashion is to use open and closed string duality. Open and closed string duality means that we treat the sphere diagram as an open string diagram where the open string swinging around in one loop fashion and ends on the conical surface. So we can treat this as a trace. And by treating this as a trace, it gives a microstate interpretation to the generalized entropy. So for topological strings, we were able to show that in fact, these microstates correspond to entanglement branes that cuts these closed strings into open strings. So I want to give an overview of what we did in these papers. We considered entanglement entropy in the A-model topological string theory using Gopakuma-Vafa duality as a topological analog of ADS-CFT. The role of the bulk closed string geometry is played by the resolved conifold, and there is some B-field flux through some S2 in the geometry. And on the open string side, the dual geometry is a deformed conifold where the flux has been turned into a large n number of branes. This is very similar to ADS-CFT. What makes this duality useful is that we know the string field theory on both sides. On the closed string side with the A model TQFT, and on the open string side, we have the UN Chern-Simons theory, A large M. We defined a notion of generalized entropy and Harlow-Hawking states for the topological string. And then we applied extended topological quantum field theory methods to factorize the bulk closed string Hilbert space and gave a canonical calculation of this generalized entropy on both sides of the duality. It turns out that the edge modes are anyons that transform under a quantum group symmetry. And we were able to realize Susskind and Uglum's idea that the generalized entropy of closed strings should be viewed as the thermal entropy of open strings that end on entanglement branes. The final thing I want to say is that in the course of studying topological strings, we solved a problem that also comes up in JT gravity, which is to give a trace interpretation of the disk partition function. Now, this doesn't look like a trace because it doesn't have a non-contractible cycle, but we could, if we wanted to, remove this small disk in the center by doing the path integral over it, leaving a hole here with some boundary condition. Now, the problem is that in both JT and topological string, when you do the path integral over this little disk, you don't get a local boundary condition, and so you don't get a trace interpretation. However, if you insert this operator D here, then you do get something that looks like a trace. In JT gravity, this D here was viewed as a de facto operator. However, we found in our extended TQFT formulation that there's a quantum group symmetry explanation for this de facto operator. And in fact, we obtain exactly the same formulas as is obtained in JT gravity for the entropy, except that we were able to give a complete symmetry explanation for this object that's inserted in the trace. So I think I'll stop there. And if you have any questions, please ask me during the discussion.
Great. Thank you very much, Gabriel, for the wonderful talk. The next speaker today will be Cixia Wei from the Yukawa Institute for Theoretical Physics, who will tell us about codimension 2 holography for wedges. Hi, Cixia.
Okay, thank you very much. So can you see my screen now?
Yes, we can see.
Okay. So thank you to the organizers for giving me this chance to speak here. Today I'm going to talk about codimension 2 holography for wedges. And this talk is based on this paper published last year, which is a collaboration with Ibrahim Akol, Yuya Kusuki, and Tadashi Takeyanagi from YITP. So please also refer to Tadashi's lecture yesterday, which gave a very good introduction to the backgrounds of this study. Okay, so I would like to start with a very brief introduction to the backgrounds. So we know that the ADS CFT correspondence is the most well-studied concrete example of holographic principle. It states that the quantum gravity in a d+1 dimensional asymptotically anti-de Sitter spacetime in ADS, which is ADS, is equivalent to a d-dimensional conformal field theory. And this ADS CFT correspondence is a codimension 1 holography in the sense that the ADS has one more dimension than the CFT. So a very natural question is that can we have, for example, a codimension 2 holography? And we would like to answer this question positively by explicitly constructing a d+1 dimensional gravity in a wedge, which is equivalent to a d-1 dimensional CFT. And to do that, let me review the ADS construction. That is when we consider some boundary CFT, which is a CFT defined on manifold with boundary, and let us consider some holographic CFT. Then its gravity jewel should also have some boundary. And to do that, we introduce some end of the Waldbrun in the gravity jewel. And by using this, let us derive the wedge holography, which is the codimension 2 holography we constructed. Let us start with a CFT living on sigma, which is the d-dimensional flat spacetime. And that is equivalent to a d+1 dimensional ADS spacetime gravity. And then I would like to introduce a boundary to sigma. Corresponding, we should also introduce an end of the Waldbrun Q1 in the ADS spacetime. And I want to introduce another boundary to sigma. And then the gravity jewel turns out to be a portion of ADS with two branes, Q1 and Q2. And then let's us just bring the two boundaries of sigma closer and closer. And as a result, the sigma turns out to be a d-1 dimensional flat spacetime, where the gravity jewel is a d+1 dimensional wedge region, W, sandwiched by Q1 and Q2. And this is what we call a wedge holography, and it is clearly codimension 2 holography. And a take-home message I want to make is that we construct a codimension 2 holography using the wedge structure in ADS. Okay, and let me just give a very intuitive explication why such a wedge holography should hold. So to do that, we'll remember the Brainwald holography, which states that a gravity living on d+1 dimensional ADS spacetime with end of the Waldbrans should be equivalent to another gravitational theory living on the branes. So from this point of view, the wedge holography, which is a gravity in the wedge region W, is equivalent to another gravity in Q1 and Q2. And now we can see that Q1 and Q2 are two branes, which are ADS spacetime themselves. So by applying the ordinary ADS-CFT correspondence, we know that the gravity on these two branes are equivalent to some d-1 dimensional CFT on sigma. And here I show three pictures which summarize the three perspectives of this wedge holography. Okay, that's I want to talk about. Thank you very much for your attention, and any questions are welcomed after the Gong show. Thank you very much.
Great, thank you very much, Cynthia. We will move now to the next speaker, who is Takato Mori from Sokendai, who will tell us about a general formula for entanglement entropy in interacting theories. Takato.
Is my screen shared?
Yes.
Okay, so, okay. I will talk about entanglement entropy in interacting quantum field theories based on my work with Satoshi and Katsuta. It's in preparation by which it should appear soon. And entanglement entropy is apparently a very important quantity in physics. And also, you can see it in Tadashi's lecture and Henry's lecture as well. But in case of conformal symmetry is absent, for the non-conformal symmetries, there are only a few works on entanglement entropy, particularly in free quantum field theories or large and supersymmetric. So I'd like to discuss model-independent study of entanglement entropy in interacting quantum field theories. For the interacting case, you need to consider what kind of UV structure entanglement entropy is given by interaction, because interaction involves somehow renormalization. So of course, we need to express the entanglement entropy in terms of renormalized quantities. And also, of course, interaction involves deviation from Gaussian. So what kind of deviation is here in entanglement entropy? And to study these things, for simplicity, we consider a scalar field on a half plane like this. This is d-1 dimension, and one dimension is in perpendicular to the boundary of region, and also this is a time direction. And we showed three things. That is area law holds that to all orders, and also perturbative resummation, and express the entanglement entropy in terms of exact 2-point functions. And last, we show some non-perturbative calculation based on the 2PI formalism. First, we use a replica trick and an orbifold method. Orbifold method is introduced by these people, and essentially, we just analytically continue replica trick, replica parameter n to 1 over n, capital N. So entanglement entropy can be expressed in terms of free energy, and this Zn on the Zn orbifold, and Zn action is given by this G hat. After some calculation eliminating redundancies, we can show that this free energy consists of this kind of bubble diagram with L loops. And what is important here is this trivial 1 over n factor, and also this delta function. Because when the argument of delta function is 0, combined with this Vd minus 1, it gives volume term. But because the factor is 1 over n, it doesn't contribute to entanglement entropy. Otherwise, that argument of delta function is non-zero, and this will give a area term. And this holds to all orders, so this is a simple derivation of area law. Second, we consider perturbation, and this by twisting, we need to insert twist for each loop momentum. But when we consider single and simultaneous twist, this leads to vanishing 2-dimensional momentum. And resumming these diagrams, results in this particular expression in entanglement entropy. And this is expressed by exact 2-point function. And this is as a result of renormalization. And third, we apply 2PI formalism. This is there is a known technique, so-called 2PI effective action, or this is a free energy. And this is known in non-equilibrium physics. And this G is related to by this gap equation. And this G is actually exact 2-point function. And using this, this is exact with an interaction. And using this one, we identify the entanglement entropy has this expression. And we know this these 3 terms contribute from contribution from exact 2-point function, while the last term is contribution from higher point function. And this first one give a area term, a term proportional to area. And the other terms is somehow counter terms and eliminates the volume term. And in general, there could be more complicated contribution from vertices, but it's under investigation. And here's a summary, and here's some open problems. So we need to consider contribution from higher point functions, and also the maybe we can modify or perturb subregion. And also practical application is like a non-perturbative calculation of entanglement entropy. That's all. Thank you.
Great, thank you very much, Takato. We will move now to the next speaker, who's Sang Yeon Bak from Wanju Institute of Science and Technology, who will tell us about holographic teleportation in higher dimensions.
Okay, thank you. Can you see my screen?
Yes.
Okay, let's start. Thank you for having me. My name is Sang Bak from GIST. Today, I'm going to talk about holographic teleportation in higher dimensions. Here, holographic teleportation means the traversable wormhole. Here is my collaborators. Let me give you an overview of the idea. Gao and Gabriel Wong first consider the two-sided black hole, which are dual to maximally entangled state in the boundary. When we consider the signal from the left boundary, it cannot touch the right boundary. This means the left and the right side of the bulk is causally disconnected. To send the signal, consider the boundary perturbation, which may shift the horizon in the bulk. The orange line is shifted horizon. Then one can send the signal from the left boundary to the right boundary. This is the idea of a traversable wormhole. To generalize in higher dimensions, we consider Lindler ADST plus 1 spacetime. The action and metric is here. And then we can prepare the entangled state on the boundary. Then we need to induce boundary perturbation that is given by the non-local interaction between two boundary operators. This causes the shift of the horizon by the delta V here. Note that this is directly related to the negative value of averaged null energy, which means Anek violation. This is constant with the traversability, so we will focus on the Anek violation. How to compute Anek? We will treat the signaling process as scattering between positive shock and negative shock. Let's move on to the picture. The blue line is positive shock as a signal, and the red line is negative shock induced by the double trace operator. Consider the two-sided correlation function of the positive shocks with the effect of negative shock here. Then one can read off the Anek in the phase shift of the correlator. Also, non-zero value of the correlator means the correlation between two boundaries. This is the result. We could find the analytic form of Anek in higher dimensions, which results in Anek violation, even in the higher dimensions. Also, we could find that the absolute value of the Anek is decreased for increasing space-time dimensions of order 1 over d. More interestingly, we could find that the interplay between traversability and scrambling. Look at the shaded part of the correlator. This is boundary perturbation term. When the denominator is 0, the boundary perturbation dominantly contributes the non-zero value of the correlator. This could be denoted by the zero lines of the denominator in the plot of t versus x. Consider the case when the boundary perturbation is initially localized at t equals 0 and x equals 10 in the red dot, then shaded region should have non-zero value of the correlator. This is the interpretation. There should be a scrambling time where the effect of boundary perturbation first arises. In addition, the causal influences of the boundary operators propagate by the butterfly velocity. This can be denoted by the slope of the orange line in the right picture. In sum, we could get the analytic form of ANEC in Lindler ADST plus 1 CFD. We could find the dimensionality of ANEC. Also, we could specify the interplay between traversability and scrambling. Thank you for listening.
Great, thank you, Sanya, very much for your talk. The next speaker is Jan Boruch from University of Warsaw, who will tell us about path integral optimization from Hartle-Hawking wave function.
Hello, can you see my screen?
Yes.
Okay, so let me start. So thank you to the organizers for giving me this opportunity to give the talk. My talk will be based on on my recent work in collaboration with Paweł Caputa and Tadashi Takayanagi. So let me first recall what is path integral optimization. So path integral optimization is the procedure in which we look for the optimal coarse graining of our Euclidean path integral, which prepares our state in field theory. So the procedure starts with the Weil transformation, which under suitable assumptions changes our state only by the factor of e to the Liouville action. Minimizing then this state with respect to our conformal to our field phi, which enters our conformal factor, allows us to find the optimal geometry which prepares our state. This can be interpreted as the optimal geometry formed by the tensor network, which optimally prepares your state. And the important observation is that this, in the simplest example of flat space, this optimal geometry coincides with the canonical time slice of ADS space. And what we did in our recent work, we wanted to investigate the path integral optimization on the gravity side. Our proposal is to consider a Hartle-Hawking wave function deformed by the introduction of a bulk brane with tension T. And then to optimize this deformed Hartle-Hawking wave function with respect to the location of our bulk brane. So let us see how it works on the simplest example in Poincare coordinates. So introduce our brane by z equal to f of tau, and then let us semi-classically evaluate the Hartle-Hawking wave function. So we do this by computing the on-shell gravity action together with the brane tension contribution. Varying now this action with respect to the to our field F, which describes our brane, we obtain equations of motion. which give us for negative tension, which give us this solution. Now to connect this story with our CFT side, with the Liouville story, we introduce uniformized coordinates on the induced metric of the brane. So we define the coordinate W as such, together with the field phi. With these definitions, the induced metric on the brane takes this suggestive form. And what's more, we can see that that our conformal factor in front of our metric takes precisely the form which we've seen previously on the CFT side for the simplest example, after relating the cosmological constant from the Liouville action to the brane tension parameter, and relating treating the W coordinate which we introduced as the Euclidean time coordinate of the optimized CFT path integral. So in this way, we have optimized. We have obtained a class of optimized metrics, optimized CFT metrics from purely from a bulk prescription. So just a few quick comments. It's important to say that we can very simply and similarly perform this this procedure in higher dimensions. So this points us to some possible generalizations of the path integral optimization procedures to higher dimensions. What's more, we obtained a class of optimized metrics for each mu, but we understand that the mu equal to 1 gives us the genuinely optimized optimized tensor network, while mu for mu smaller than 1, we regard them as partially optimized. And also we can explicitly check that our effective equations of motion for function f coincide with the equations of motion derived from the general Neumann boundary condition. Okay, thank you.
Great, thanks Jan for the wonderful talk. The next speaker is Anish Prema Balakrishnan from the Chennai Mathematical Institute, who will tell us about the first law of black hole mechanics with fermions.
Is my screen visible?
Yeah, I can see you and I can see your slides.
Yes, okay. So let me start. I'd like to first thank the organizers for giving me an opportunity to be a part of this conference. I will be speaking. I'm a graduate student at Chennai Mathematical Institute in India. I will be speaking about the first law of black hole mechanics with fermions, and this is based on work done in collaboration with these authors. So let me start. So the basic idea is that there is this higher world formalism, and it gives us a way to derive the first law of black hole mechanics. And the idea is that you work in the covariant phase space of your theory, and you can define the perturbed Hamiltonian charge by the following formula, where sigma is a Cauchy hypersurface and q xi is the Noether charge corresponding to xi. This theta is the variation, is the boundary term that you get when you vary the action. Now, once you have this formula, what you can do is you can choose a hypersurface that is hinged at the bifurcation surface and at infinity, and then choose the horizon generating Killing field for the xi, and this formula basically reduces to this. And this is nothing but the first law of black hole mechanics. And here on the left hand side, you have a more general expression for the entropy of the black hole. However, this doesn't work for generic gauge field configurations. In fact, even for pure first order gravity, and it certainly does not apply if fermions are present in the theory. More precisely, one can explicitly calculate the Noether charge for first order gravity, and you have the following form. And naively, this vanishes on the bifurcation surface because the horizon generating Killing field K vanishes on the bifurcation surface. No, but this is an erroneous result because omega is actually divergent, and one can carefully evaluate this in a limiting procedure and show that this is actually finite, and you get the correct expression. Now, a more general resolution to this problem can be achieved by generalizing the covariant phase space to principal fiber bundles, and there you work in the space of all Weyl binds and connections in the theory. Alternatively, you can covariantize the Lie derivative with respect to internal symmetry transformation and define a new derivative to define stationarity and generalize the formalism appropriately. And this is what we also use. Now, it's nice that the two approaches match when the projection is made from the bundle to base space. Now, the question that we want to ask is in the formalism proposed by Prabhu, he shows that the first law of Blackwell mechanics is not modified in the presence of Dirac fermions. A natural question is whether this is true for all fermions generically. And one should contrast this with the case of bosons. While the scalar field does not contribute to the first law, the vector field indeed does contribute. And since the Reiter-Schwinger field is a vector spanner, it is an interesting theory to look at. And the question is, does it modify the first law? Now, let me give the punchline up front. We showed that the answer to this question is negative. Briefly, what we did is we generalized the Airwall formalism by covariantizing the Lie derivative to the Cosmet derivative. And we call the Noether charges obtained from this the Lorentz diffeomorphism Noether charge. We calculate the Lorentz diffeomorphism Noether charge for the Majorana fermion as a warm-up, and then try to find the Lorentz diffeomorphism Noether charge for the Reiter-Schwinger field coupled to gravity. And in both these cases, we find that the Noether charge is indeed modified by the presence of these fields, but they are still vanishing at the bifurcation surface and therefore don't seem to affect the first law. But for the purpose of this talk, let me be very brief and just show directly the case of simple supergravity. And for that, we need to know what the Cosmet derivative of the objects of interest are. And for the Reiter-Schwinger field, the Cosmet derivative has the following form, where this is nothing but the usual Lie derivative, and then you have an additional term. And the Cosmet derivative for the spin connection has the following form. And the Lagrangian that we choose to work with has the following form. This is with the Reiter-Schwinger, the matter part, and the rest is gravity. And the total Noether charge is a sum of the gravity sector and the contribution from the matter sector. And the expressions are given here. Now, notice that the change from pure gravity is the terms highlighted in red. And this object K is called the contortion tensor and is proportional to linear combination of the torsion tensor. And in the case of pure second order gravity, where there is the vanishing torsion, this is nothing but the usual star decay evaluated at the bifurcation surface. Now, as I mentioned earlier, the first law is given by the following formula, and the difference, and I also told you that the difference between the usual, the pure gravity and the simple supergravity are terms that go like this, and both of which vanish on the bifurcation surface because the Reiter-Schwinger field is assumed to be smooth. Now, and the contribution from pure gravity at the bifurcation surface is the usual T delta S. And at infinity, in the standard boundary conditions, the only contribution is the ADM mass and the ADM angular momentum. And hence, we obtain the result that the first law is not modified and is just the usual first law. And with that, I'd like to thank.
Great. Thank you, Nish, for the wonderful talk. Our next speaker is Siyu Lee from the University of Michigan, who will tell us about microscopics of BPS and near BPS black holes in ADS3.
All right, can you hear me?
Yes, I can hear.
Yes, great. So I'd like to thank the organizers for this opportunity to present my work with Finn Larsen. This talk is based on this extremely fresh paper, which announced last Friday. Recently, there has been progress in microscopic accounting of Bekenstein-Hawking entropy of supersymmetric ADS black holes in various dimensions. In particular, I have ADS 5 in mind, but what I say essentially applies to any of ADS 4, 6, or 7 as well. The key has been the entropy extremization principle, which is basically a statement that once you have a partition function defined from the field theory side as a trace over the Hilbert space, you can expand by charges and get the degeneracies, which will tell you the entropy. And the calculation of this partition function in some limited regimes has been done in 2018 by these people. But this formula is valid only for a set of potentials that satisfy this constraint, which requires them to be complex in nature. Of course, this formula is what makes the partition function the superconformal index. It's a beautiful mathematics, but the potentials being complex blurs the physical interpretation. So let me tell you just one thing that's mysterious about this complexity. Performing the entropy extremization naively to calculate the degeneracy as a function of charges over here, it is complex in general, So that's normal, but by requiring for some unknown reason the result to be real, it puts an extra constraint on the charges. And that turns out to be the exact relation satisfied by gravity solutions. This constraint is important because only after imposing this extra constraint, you happen to recover the Bekenstein-Hawking entropy. In other words, all the results people ever get from this partition function are valid modulo the constraint. Our goal is to solve this mystery by looking at the same problem in a much simpler and better understood setting, which is ADS3 CFT2. So we look at ADS3 black holes due to 2D CFTs with 4,4 supersymmetry. We similarly define a grand canonical partition function, which is designed to describe BPS black holes in ADS3. And it turns out that in CFT2, we have an explicit formula for that partition function, which looks like this. In particular, notice that the omega L tilde, this potential appears linearly in this partition function. And from the thermodynamic partition function, it is easy to evaluate the macroscopic charges using a familiar formula like this. And then we easily get the relation JL equal to KL from this partition function, where KL relates to the left sector central charge. This is in fact the precise relation known to be satisfied by BPS black holes in ADS3. Now we can play with this partition function as people do with ADS5, imposing this complex constraint on the potentials that convert the partition function into the superconformal index, elliptic genus in this case. Then the log Z looks like this, which is extremely analogous to what we've seen for the ADS5. So we perform the same entropy extremization, which tells us to extremize this function. Then as a result, we get this as our entropy. By requiring this imaginary part to vanish, we do recover the charge constraint, and only then the real part reproduces the known result for ADS3 black hole entropy. But as I have motivated, this is weird. Since JL and KL are integers, there's no reason to disallow this imaginary term because e to the s will be real anyways. Our resolution of this mystery is the following. Let's find out how this entropy acquires its imaginary part. It is entirely due to this complex condition where omega L gets the imaginary part minus pi, which carries on to the s because it's a linear function of omega L. So imaginary part of s precisely encodes its dependence on the potential omega L. Then requiring this to vanish requires the partition function to depend on omega L like this, which is the simple thermodynamic formula that we use to derive the charge constraint. Let me quickly throw in another interpretation of the charge constraint that is purely microscopic. We look at the representation theory of 2D n equal 4 superconformal algebra, which is relevant to our field theory. Here, all states in the Hilbert space are labeled by these two eigenvalues, so we can map them on a two-dimensional plane like this. It turns out that for any unitary representation, a state here with these eigenvalues pairs up with another state here with these eigenvalues. And you can see that their J eigenvalues always average to K. So the charge constraint is what is satisfied by averages of the spectrum, but not by individual states. That's all I have to say, and please feel free to ask questions or look up the paper. Thank you.
Great, thank you, Seal. Our next speaker is Zhuoyu Xian from the Institute of Theoretical Physics, who will tell us about complexity growth of operators in the SYK model and in JT gravity.
Okay, can you screen?
We can see your screen.
Okay. Thank you, Glenn, for giving me this opportunity to speak, to keep a talk here. I will introduce my recent paper with Sokajian and Swingo and about the complex growth of operator in the SYK mode and JT gravity. First, we will talk about the operator growth. For non-integral Hamiltonian, if we given a simple operator and we evolve it, it will become more and more complicated since since the operator is non-commutative with the Hamiltonian, and you can think that the conjugate to build this complicated operator will become more and more complex. And we may have the two quantity to describe this process. The first is the so-called the size operator size. Another is operator complexity. We may think that is the size is related to the minimal section of gate, and the complexity related to the minimal number of gate. So we may expect such a relation like this. The growth ratio of complexity will proportional to the size change. Okay. We may check this formula and calculate the behavior of complexity and operators in the SYK model and the generic gravity. But before that, we will introduce a notion about partially entangled thermal state. We will consider a copy of Hilbert space and build a maximally entangled state on it. And we will map the operator on one side to a state in such the double copy of Hilbert space like this. And the identity operator is mapped to the thermal state, and we may consider some simple operator and map it to the state. And we will consider such states in generic gravity and in the SYK model. In the SYK model, it captures the size of such states. It grows exponentially first and then saturate. And you can see this figure. And we also can calculate the complexity in the SYK model following the proposal of K complexity. We will design some Lewisian which evolve the operator and evolve the state. And but we can expand an operator on some so-called K basis. The K basis is Smith formalization of such operator list. So finally, we can also calculate the complexity of such operator. And in the SYK model, we find that the behavior of complexity like this, it grows exponentially first and then linear growth. Which agree with our expectation that the growth ratio of complexity is proportional to the operator size. Here is our numerical calculation, which agree with our estimation. Okay, finally, we will go to the calculate the complexity in generic gravity. Here we will use the complexity volume proposal proposed by Susskind, whereas complexity is proportional to the volume connecting the two boundary. But it has two cases. The volume is just proportional to the dilaton field times to the geodesic length. So we can when the geometry is back-react by the operator, we insert in the buck, and then we calculate the geodesic length like this, and we find that in linear growth, and finally saturate, and finally it grows exponentially and then linear growth. So in conclusion, we in both SYK model and GT gravity, we find that the complexity show exponentially growth to linear growth behavior, and then we find that their growth ratio are proportional to the size of chain. Thank you. That's all.
Great. Thank you, Joa Yu, for the nice talk. Our next speaker is Boyoung Yu from the Yale Mathematical Science Center, who will tell us about ADS gravity and complex SYK models.
Thank you. Can you see my slides?
Yeah.
Is it full screen?
Not yet.
Okay, nice.
Yeah, now it works.
Okay. First of all, I would like to thank the organizers for giving me the opportunity to share my recent work on ADS3 gravity and the complex SYK model. It's based on a recent paper in collaboration with Pankaj Chaudhary Yanis Dimitri and Wei Song. I would like to begin by a brief review of the complex aspect model, which is involves a large number of complex fermions interacting with each other with the following Hamiltonian. And the effective action of this model can be expressed in terms of the two-point function G and the self-energy. The saddle point equation motion is given like in this equation, which is also a string density equation. And in the low energy limit, this equation is solvable, and the CSVK model will have very interesting properties, some of which can be comparable with the warped conformal field theory. For example, the symmetry of CSVK in IR limit has this time repenetration and phase shift symmetry, which is very similar to the real cosmology symmetry in warp CIT, except that it's broken to SL2 cos UY in the CSVK. And the effective action of the CSVK at low energy limit consists of the Schwarzen action and plus an additional U1 anomaly term, which can be comparable with the real generator in warp CFT. And also, if you calculate the one loop correction to this partition function using this effective action, you will receive a contribution which scale as temperature to the -2, which also matches the vacuum character of CFT. And motivated by this similarity, we investigate the pure ADS3 gravity as a candidate of the holographic view of CSVK model. And the general solution can be expanded in this Feynman-Graham gauge, and the solution space is all determined by the boundary metric, which is G0. And we are considering a so-called deformed CFT phase space, which is parameterized as this equation. And remember that if mu plus equals 0 and you impose the CSS boundary condition, the theory is due to warp CFT. But here we turn on this deformation parameterized by mu plus so as to break the symmetry slightly, and that's what happens to CSVK model. And after determining the phase space, we come to the boundary conditions. And so we first wrote down the version principle, where the first line is the rewriting of Tij.Gij. And in the second line, we perform a canonical transformation, which is characterized by this spectral flow function called R, which is very important in our paper. And as a generalization to CSS, we also add this parity violating boundary term. It plays the role of a long transformation, and then you arrive at this following boundary conditions now. And then we perform this consistent KK reduction with this ansatz, and the resulting theory is described as by this 2D S10 Maxwell dilaton action. And such action have two types of solutions. One is a random dilaton solution, and the other is a constant dilaton solution. And some important facts about these two solutions are both solutions can be uplifted to 3D. And if you compare with the boundary metric of the form CFT space, you find that the random dilaton solution, when it's uplifted to 3D, it corresponds to a non-zero mu plus. And the uplift of constant dilaton solution has 0 mu plus. And then we can construct an exact interpolating flow from the solution to the constant dilaton solution. And the constant dilaton solution can be obtained using this extreme limit, mu plus to 0. And this flow can also be understood from 3D point of view as a neo-Hessian expansion. So it's a UV IR flow. Then we can calculate its 2D effective action, which is given by the sum of 2D renormalized action plus this additional parity violating term. And if you use the right solution and expand in mu plus, you find the linearized part also consists of a Schwarzen term, U1 anomaly term. Our nu 0 is the boundary value of the dilaton, which is of order mu, and CK are central charge and level respectively. And then it's very straightforward to see that this coincides with the effective action of CS model, provided identification. And you can also check that thermodynamics can also be reproduced by studying the extreme mobility black hole. And as a summary, I would like to show this picture in our paper. So we start from the 3D as singularity and impose the generalized CSS boundary condition. And by holographic duality is to be due to some deformed CFT. And you can do the dimension reduction and all these three elements will flow to the same theory described by Schwarzen plus the additional U1 anomaly term. And this as a deformation of Wapsati theory. Okay, I'm done. Thank you.
Great. Thanks, Boyan, for the nice talk. Our next speaker is Yi Li from Fudan University, who will tell us about TT-bar CFT and cutoff ADS.
Okay, let me share my screen. Can you see me now?
Yes.
Okay, great. So good afternoon. I'm Yi from Fudan University. It's my pleasure to be here talking about TT-bar CFT and cutoff ADS. So I will first show the TT-bar flow equation for large C CFT. And based on that, we compute the sphere partition function and entanglement entropy. And we derive the cutoff ADS holography in the pure gravity sector. So first of all, the TT-bar deformation is a deformation by the TT-bar operator, which is quadratic in the energy momentum tensor in this covariant form. It has many interesting properties, so it's natural to ask what the holographic dual of TT-bar deformation is for holographic CFTs. And by treating the TT-bar deformation as integrated double trace, infinitesimal double trace deformation, Guika and Mountain derived the TT-bar flow equation in the large central charge limit for the generating functional, for the metric, and for the one-point function of energy momentum tensor. And the solution is given below. Using the TT-bar flow equation, we can compute the partition function of TT-bar CFT for a sphere of radius r, and it takes this form. And also for the entanglement entropy of antipodal points, which takes this form. In comparison with the previous result obtained by Donnelly and Shia, our result has a well-defined CFT limit as the deformation parameter goes to 0. And as the deformation parameter goes to infinity, our result grows without bound instead of going to 0. For the cutoff ADS holography, a generic setup for cutoff ADS holography would look like this with the GKBW relation. But instead of going to the asymptotic boundary of ADS at rho is equal to 0, we set a finite cutoff at rho C. In addition, we restrict to the pure gravity sector. On the field theory side, that means we do not turn on sources conjugate to other operators in the generating functional. The easiest way to see the cutoff ADS holography is by the flow equation of the on-shell gravity action. So the flow equation of the on-shell gravity of the on-shell action as the cutoff surface moves in the direction of normal geodesics can be shown to take a TT-bar form. In addition, it actually corresponds to the flow equation, TT-bar flow equation of the field theory generating functional if we identify the TT-bar deformation parameter lambda with the cutoff position with this formula, modulo local counterterms. And we can show that in dimension 2, we don't have to add those local counterterms. In addition, we can also show that the TT-bar flow equation of the metric and the one-point function correspond to the flow equation of the boundary metric and Brown-York tensor as the cutoff surface moves inward. We also have holographic computation of the sphere partition function, which we computed on the field theory side previously. So a few remarks. The cutoff ADS holography we derived only works for pure gravity sector. In fact, we don't expect it to work when the matter fields are included. It's certainly a good question to ask what the full cutoff ADS holography would be. In addition, we also want to understand the divergent behavior of the sphere partition function or entanglement entropy when the deformation parameter goes to infinity. We want to understand its physical interpretation, especially its relation to non-locality of the TT-bar deformation. Thank you for listening, and email me if you have any questions.
Great, thank you for the nice talk, Yi. Our next speaker is Junichi Haruna from Kyoto University, who will tell us about thermodynamics of TT-bar deformed ON vector model.
Okay. Let me share the slide. Okay. Can you see the slides?
Yes.
Okay. Thank you for introduction. I'm Junichi Haruna from Kyoto University, Japan. First of all, I thank our organizers for giving me this opportunity. Today, I talk about thermodynamics of a kind of irrelevant deformation called TT-bar deformation of the ON vector model. This talk is based on a work in progress with Katsuta Sakai in KK and Kentaro Yoshida in Kyoto University. You can see the paper with them and Takaaki Ishii and Hikaru Kawai as a reference. First, I explain what is TT-bar deformation. TT-bar deformation is an irrelevant deformation of two-dimensional quantum field theory, as suggested by these papers. And it follows a TT-bar flow equation. Its infinitesimal form is this one, and its differential equation form is this one. Here, L alpha is a deformed Lagrangian, and alpha is deformation parameter whose mass dimension is -2. And here T mu alpha is energy momentum tensor defined from L alpha. This equation means that the TT-bar deformation is adding the determinant of energy momentum tensor to the Lagrangian. Why TT-bar deformation is interesting? For example, TT-bar deformation of the free massless ON vector model is the Nab-Goto action in static gauge. Its Lagrangian is given by here. Here, alpha is the deformation parameter alpha is regarded as the string tension. And also, it is known that the TT-bar deformed energy spectrum on the cylinder satisfies the first implicit Vargas equation here. En alpha is energy eigenvalue of nth eigenstate, and Pn is momentum of the eigenstate, and R is the circumference of the cylinder. And also, there are many interesting properties of TT-bar deformations. And I gave you the motivation under our work that, as you see before, TT-bar deformation has many interesting features. But we know that irrelevant theories should have some inconsistencies as quantum field theories. So there is a gap, and we want to know why TT-bar deformation works well. In order to do that, we calculate the thermal free energy of the TT-bar deformed free massless ON vector model in two ways, from the path integral and the Vargas equation, and compare these results. And here is the result. By path integral, we consider the larger limit, and the leading order contribution to the thermal free energy density is here. Here, beta is inverse temperature. We also obtain it from exactly from TT-bar deformed ground state energy by solving the Vargas equation, like here. Let's move on to the summary and discussion. The results are the same. But how about subleading contributions? The results from the larger limit has one over corrections, while the one from the Vargas equation does not. So this fact suggests that there are miraculous cancellations of the one-level collections. And now we are going to investigate at this point these miraculous cancellations further. This is the end of my talk. Thank you so much.
Great. Thank you, Junichi, for the nice talk. And thank all the speakers today.